In order to understand the thermodynamic derivation of law of chemical equilibrium, the very first thing we need to understand is Gibbs free energy or free energy. So what is Gibbs free energy? Gibbs free energy is capacity of any system to do work. Capacity of a system to do work. All right. Now the notation for Gibbs free energy is, we write it in the form of G. Now there is one thing with the Gibbs free energy. It depends on pressure and temperature. Depends upon pressure and temperature. And we cannot measure the absolute value. So absolute value of Gibbs free energy cannot be measured. But we can measure the difference, or we can say we can measure the change in Gibbs free energy. That is delta G can be measured. Now for any chemical reaction, what happens if you have to measure change in Gibbs free energy? So that is given by delta G is equal to free energy of product minus free energy of reactant. So for any chemical reaction, change in free energy is given. So this is for any chemical reaction, the change is given in such a way. We can also write it as Gibbs free energy of product minus Gibbs free energy of reactant. Now since we cannot measure the absolute value of Gibbs free energy, so we need to convert it into something else. So the new term comes is chemical potential. Chemical potential, it is nothing but free energy per mole. Chemical potential is free energy per mole, and it is denoted by this symbol, and this symbol is called mu. So if we have to write down our change in Gibbs free energy in terms of chemical potential, so we will write it as number of moles of particular product. Let's say we have a general reaction, plus so on, x plus y plus so on. Let's suppose this is our general reaction. Now we have to write down our Gibbs free energy in terms of chemical potential. So we will write it as delta G is equal to Gibbs free energy of product, that is given by number of moles of X into chemical potential of X, plus similarly number of moles of Y, chemical potential of Y, and so on, minus number of moles of A into mu of A plus B mu of B plus so on. So this is our Gibbs free energy represented in terms of chemical potential. So these terms, these are chemical potentials of X, Y, A and B respectively. So this is when we represent the Gibbs free energy in terms of our chemical potential. Similarly, if we have standard chemical potential, how do we represent it? First thing, what is standard Gibbs free energy? Standard Gibbs free energy is Gibbs free energy of any reaction at standard temperature and pressure condition. So this is represented by delta G naught, delta G of product minus G naught of reactant. Now similarly, if we have to represent it in terms of chemical potential, so we will take standard chemical potential here, so on, minus that of reactant, that is A, chemical potential of A plus B, so like that. Alright, so let's say this is our first equation and this is our second equation. So we are going to use these equations further in our derivations. The next thing that comes here is delta G values. All of us know that delta G is equal to 0 at equilibrium. That means the Gibbs free energy of product becomes equal to that of reactants at equilibrium. That's why delta G is equal to 0 at equilibrium. And all of you must have studied this. A reaction is spontaneous when delta G value is negative. So there were two things. Delta G is equal to 0 at equilibrium, and delta G is less than 0. That means reaction is spontaneous. All right. Now let us consider a closed system having a reversible reaction. And let's say the reaction is A plus B plus so on to give you X plus Y plus so on. All right. And let's say these are chemical potentials of reactants. Similarly, mu X, mu Y are your chemical potentials of products. This is at constant temperature and pressure. Now we have to find out the change in free energy. Change in free energy of this reaction at constant temperature and pressure. So if we have to write down the total free energy of reactant, total free energy of reactant, that would be number of moles of A chemical potential of A plus number of moles of B into chemical potential of B, and so on. Similarly, total free energy of products will be X mu of X plus Y mu of Y plus so on. So if we have to find out change in free energy, so that will be change in free energy of reaction at constant temperature and pressure. That will be delta G equal to total free energy of product minus total free energy of reactant. And if we put the value of free energy in terms of chemical potential, it will become X of mu X, Y of mu Y plus so on. That is for products minus A of mu A plus B of mu B plus so on. This one is for reactant. Now this is the same equation we had previously as 1. Now at equilibrium, our delta G is equal to 0. So putting this value of delta G in equation 1, what you're getting, X of mu X plus Y of mu Y plus so on minus A of mu A plus B of mu B plus so on is equal to 0. Alright. Now take the reactant term to the right hand side. Alright. So what you will get? You will get X of mu X plus Y of mu Y plus so on is equal to A of mu A plus B of mu B plus so on. Now there's one new thing. The chemical potential for constituents of a gaseous mixture are given by an equation. Mu is equal to mu naught plus RT ln A. This A could be anything. This is activity, so it can be partial pressure or concentration. Anything that signifies as activity, that can be used here. So this is nothing but chemical potential of constituents of a gaseous mixture is given by. So here this mu is your chemical potential, mu naught is your standard chemical potential, R is your real gas constant, T is temperature, and ln A is your activity, that can be your partial pressure or concentration. All right. Now I'm going to use this equation and make changes to the equation number 4. So I'm giving this equation a number, that is 4. Now if I write the fifth equation in terms of partial pressure, let's say partial pressure, that then mu becomes mu naught plus RT ln P. All right. And if I write this equation individually for all the reactants and products, it will be written like this. Chemical potential of A will be equal to standard chemical potential of A plus RT ln partial pressure of A. So similarly, we can write this equation for all the reactant and products. So let's say this is our seventh equation collectively. Now what we are going to do, we're going to put all these values to our equation number 4. So I'm going to write the equation number 4 again and then going to put all these equations. So our equation number 4 is x of mu of x plus y of mu of y plus so on equal to a of mu of a plus b of mu of b plus so on. Alright. Now if I have to put these values, this equation will become x into mu x naught plus rt ln px plus y mu naught of y plus rt ln p of y plus so on is equal to a of mu a naught plus rt ln p of a plus b into mu b naught plus rt ln of pb. Alright, now the next thing is to take all the log terms on one side and chemical potential terms on the other side. So very first thing I'll do, I'll distribute potential terms here. X of mu naught x plus y mu naught y plus so on and plus rt x ln p of x plus y ln p of y. This is our product term. Similarly, we will distribute the reactant term a mu naught of a plus b mu naught of b plus so on plus rt a ln partial pressure of a plus b ln partial pressure of b plus so on. Now I am going to keep the RT term on the left hand side and I'll take the remaining terms to the right hand side. So RT x ln p of x plus y ln p of y plus so on minus a ln p of a plus b ln p of b plus so on. This is RT term taken on the left hand side. Now all the chemical potential terms I am taking on the right hand side. So a mu naught a plus b mu naught b plus so on minus x mu naught x plus y mu naught y plus so on. Now by condensing the log terms, we'll get RT ln px raised to power x into py raised to power, this is capital Y, y so on divided by pa of a, pb of b and so on. This becomes our left hand side term and right hand side term will remain as it is. Now you see this equation in the very beginning when we were discussing chemical potential, that time we had written an equation of standard Gibbs free energy in terms of standard chemical potential. So I'll show you here the very first discussion we had. So here we have given this equation number 2. So delta G naught is equal to x into mu naught x, that is standard chemical potential of x. So this equation was in terms of standard chemical potentials of your reactants and product. So this equation I am going to use here. So this whole term is nothing but delta G naught. But there is one thing, it is written in terms of reactant minus product. But here what we had G naught product minus G naught reactant. So here we will have a negative sign in front of delta G naught. Now if I take my RT term on the right hand side, then I'll get Px raised to power x, Py raised to power y, and so on, divided by Pa of A, Pb of B, and so on, equal to minus delta G naught divided by RT. Alright. So, and if I take antilog, then what I'll get? Px of x, Py of y divided by Pa of A, Pb of B, and so is equal to e raised to power minus delta G naught divided by RT. Now next thing that comes is this is nothing but chemical equilibrium in terms of partial pressure. What does the law of chemical equilibrium says? Law of chemical equilibrium says Kp, that is chemical equilibrium or equilibrium constant in term of partial pressure is equal to product of partial pressure of your products raised to stoichiometric coefficient divided by product of partial pressure of reactants raised to their stoichiometric coefficient. So this is your chemical equilibrium constant. In terms of pressure. So using these two equations, we can write Kp is equal to e raised to power minus delta G naught by RT. Or similarly, you can write this equation as delta G naught is equal to minus RT ln Kp. So this is the relation between delta G naught, and that is standard Gibbs free energy, and your equilibrium constant. This is derivation in terms of pressure, but similarly you can derive an equation in terms of your concentration. So if you can remember, we had a conversion of chemical potential. Here chemical potential was written in terms of your partial pressure. The equation number 6 we have taken in terms of partial pressure, and if we, instead of taking this, if we take chemical potential in terms of your concentration, the derivation we will get will be in term of Kc, that means your equilibrium constant in terms of concentration. So I am going to write chemical potential in terms of concentration, that is mu is equal to standard chemical potential plus RT ln C. C is concentration. So if I write this for all the reactants and product, my combined equation will become RT ln C of A. Let's say this equation is number 14. So mu of B is equal to mu B naught plus RT ln CB mu of x is equal to mu naught of x plus RT ln C of x. Mu y is equal to mu naught y plus RT ln C of y. Alright, if we put this equation in our equation number 4, and equation number 4 was x of mu of x plus y of mu of y plus so on is equal to a of mu of a plus b of mu of b plus so on. This is at equilibrium condition. Alright, so now if we put these equation number 14 in our equation 4, what we will get? X of mu of x naught plus RT ln C of x plus y into mu naught y plus RT ln concentration of y. This is our product side, and our reactant side will become A of mu of A naught plus RT ln CA plus B into mu naught B plus RT ln CB. Alright. Similarly, what we will do, we will take the RT terms on the right hand side, left hand side. So we'll get ln C of x into its stoichiometric coefficient plus y ln Cy plus so on minus A ln Ca plus B ln Cb plus so on is equal to A mu naught A plus B mu naught B plus so on minus x mu naught x plus y mu naught y plus so on. And if we shorten our log terms, what we will get? Ln Cx raised to power x, Cy raised to power y divided by Ca raised to power a, Cb raised to power b, and so on is equal to this. This is nothing but our delta G naught as we have previously derived, and a negative sign will come because the sum of chemical potentials of your reactant minus product is written here, but delta G is Gibbs free energy of product minus reactant, so we are going to put a negative sign here. Let's say this equation is number 15. Now if we further manipulate our equation, what we get? Minus delta G naught by RT and again Cx raised to power x, Cy raised to power y, and so on divided by Ca of A into Cb of B, and so on equal to E is 1 minus delta G naught divided by RT. Now all of you know this is nothing but your Kc, that is equilibrium constant in terms of concentration. So we can say Kc is equal to E raised to power minus delta G naught divided by RT, or you can also write this equation as delta G naught is equal to minus RT ln Kc. Alright, so let's say this is our 16th equation and this is our 17th equation. This is deriving the equilibrium constant in terms of your thermodynamics. So we are getting the equilibrium constants in terms of Gibbs free energy. All right. So the two relations we have established between equilibrium constant and Gibbs free energy are given by delta G naught is equal to minus RT ln Kp, that is equilibrium constant in terms of partial pressure, or delta G naught is equal to minus RT ln Kc, that is equilibrium constant in terms of concentration. So if we know the delta G naught value of any reaction, we can calculate the equilibrium constant, or if we know the equilibrium constants, we can find out the value of Gibbs free energy of that reaction.